Thank you, Sergey, for seeing to it that I came here. I really enjoyed the celebration of Mel's career, and I want to give a talk. The room's slightly strange. You people over there, I'm not sure if you're looking at the same presentations or not, but anyway, I'll try to keep you in the loop. I had a dream, which was to present a paper based on a paper that Mel had written. Mel wrote a very nice paper called Bilattices Are Nice Things. And the title of my talk was going to be Bilattices Are Nice Things, but not as nice as Mel Fitting. But I never finished that paper that I was working on. And so I'm substituting something else, but with a few remarks about Mel at the beginning. So with that, let's start.
What is the Globalization Society?
Well, I thought you would ask. You know, there are various well-known societies, things like American Advancement, Association for the Advancement of Science, or the American Academy of Arts and Sciences,
or Flat Earth Society.
Flat Earth Society. Anyway, this is a super secret organization. Don't tell anyone, you're all sworn to secrecy. Founded by Bruce Horowitz. Mel Fitting was an early member, and I've already told you more than I should. I hope I can make it back safely this evening. If you want to know more, look for the next Dan Brown novel. But there's a membership ritual. You have to write one logical limerick that's approved by the editor-in-chief, Raymond Smullyan. I have Raymond's approval to share this limerick with you, which is the one I wrote as Fitting for my getting into this august society. Here's the Fitting limerick about my membership. There is a logician, Mel Fitting, who once proved a theorem while sitting. I thought quite a lot about that word. I wasn't sure if it should be sitting or maybe something else. So it starts with an SH, but Raymond convinced me to use the cleaner version. He jumped to his feet and ran down the street, yelling "Eureka!" before the ground hit him.
So, do you know how long it took him to hit the ground?
No.
A banana second.
A banana second? Okay. So, with that, little sort of limerick introduction, we'll go on. Traditionally, logic is thought of as timeless. I wish these screens were a little bigger, but
so do we.
I will try to speak.
They're really big enough, so for me,
traditionally, logic is thought of as timeless, static, situated in Plato's world of the forms, unmoving, like Rodin's statue of the thinker. So there's the thinker, thinking about P or not P.
But wrong.
Thinkers such as Mel Fitting have emphasized the temporal and dynamic aspects of logic. I won't mention many others, but will content myself with Aristotle and his Sea Battle Tomorrow. Von Pratt, who, 1976, I believe, introduced the phrase dynamic logic. And Arthur Pryor for his groundbreaking work on modality and temporal logic. And of course, Johann van Bentham. And I'll be talking mostly about Johann's work today. Van Bentham's work has taken many different forms, but one of the most interesting, to me at least, has been what Van Bentham has labeled aerologic in 1991. And Benham, a student of his, came out with papers about the same time, and I'm really not clear about who was the originator of aerologic, but I'm pretty clear that Van Bentham first used that name. Now, my interest could be viewed as self-serving because it stems from strong connections that I see between aerologic and the Anderson-Belknap relevance logic. So here's the dynamic thinker, not thinking about P or not P, but thinking about arrows, right, all pointing different ways to each other. An arrow frame is a structure. It's a set A, non-empty set. It has a three-placed relation, a ternary relation C on it. It has a binary relation F on it. and it has a unary relation, just a property set of arrows. So members of A are called arrows. CXY means arrow X is the composition of Y and Z, and you can see that in a diagram below. FXY means Y is the converse of X, so you've got two arrows A and B pointing in exactly opposite directions. And I of X means X is an identity arrow, which means you essentially get on the bus, and you ride around, you come right back to where you started. Right? So that's what an arrow frame is. How many have seen arrow frames before? Yeah, a number of you. For those who have or haven't, do they remind you of a Meyer frame? If you've seen Meyer frames before, we'll talk about those in a moment. The basic language for an arrow logic contains the unary connectives of negation and converse. That's that funny V thing. Van Bentham used it, and I follow him. And the binary connectives, conjunction, and we'll call it just multiplication. The connective converse is to be understood as a kind of converse, and the connective multiplication is to be understood as a kind of multiplication of relations. A model assigns a subset of A, that's the universe of arrows, to each propositional letter P. This then induces the following definition as to when a sentence holds an arrow X. Well, we'll say P holds just in case it's in the set it's been assigned to P. Not phi holds it just in case phi doesn't hold. The converse of phi holds at X just in case there is a Y, such that fxy and phi holds at Y. So that's basically saying that phi holds at the converse of Y. The conjunction holds at X just in case both conjuncts hold at X. And the multiplication of relations holds at X just in case there are two other arrows, Y and Z. So X is composed out of Y and Z, and Y makes phi true and Z makes psi true. And then X, that second X should not be there. It should just be X makes id true, ID, if and only if I of X. X makes this constant identity sentence true just in case X is one of the identity arrows. Now, Van Bentham, 1994, gave axioms for the minimal arrow logic. We'll call it MAL, not MEL. I tried to work with that, but didn't get it to work.
So this is malformed.
Malformed, okay. It's actually, I think they're very nicely formed. That was my problem. And it just has these simple properties that the multiplication distributes over disjunction in both directions, and converse also distributes over disjunction. That's all there is to it. Now, completeness for MAL follows from Janssen and Tarski's 1951 representation of Boolean algebras with operators. Since forming a Lindenbaum algebra, the usual way identifying provably equivalent formulas, we get a Boolean algebra with operators that correspond to the multiplication and the converse. That representation in a standard way will give you completeness for this minimal arrow logic. Now this I really apologize for. I'll just read it. Rotley and Meyer published their semantics of entailments 1, 2, and 3 in the years 1972-73. As with the Kripke semantics, there were a lot of competitors in the early 70s with essentially the same or very similar ideas. Charlwood, Fine, Kabay, Maximova, and Urquhart. Rotley and Meyer, though, I think get the name Rotley-Meyer semantics because of they just won by a hair in terms of time, I think, if you look at the timing of all this. But also their clarity and their persistence. So I'm going to call these Rotley-Meyer frames. Some people call them relational frames or something like that. So they have a frame and it has a set. They call setups. It's not possible worlds because these things could be incomplete or inconsistent. They call them setups. I prefer the name information state. That's where it started with setups. K is then just a set of these things. 0 is a distinguished member of K. R is a three-placed relation. Sounds familiar, right? Star is a unary operation. Well, star is there by also a two-placed relation, of a special kind. And Rotley and Meyer called the members of the K, I've already told you, the setups. They put various constraints on these frames. We're not going to explore these until later. We do note, however, they defined a binary relation, A less than B, A less than or equal to B is actually better, as just R0 AB, and gave R properties that assume that sure that less than is a quasi-order, reflexive and transitive. Now, Rotley and Meyer assume a basic language that contains the unary connectives of negation. It's a different negation, using a tilde there, as opposed to the kind of square negation that I used previously when talking about Van Bentham. And there's a reason for that. It's a different negation. We'll call it a De Morgan negation. We'll call that other classical negation a Boolean negation. And they have a binary connectives of conjunction and disjunction and relevant implication. They take evaluation V to be a function that assigns to each pair PA, where P is an atomic sentence, either T or F, and from this they inductively define a function, I, the interpretation function, that assigns to each pair phi A, where phi is an arbitrary formula and A is a setup, again, of either true T or false. No poor valued stuff here, it's all two valued. Now, an important constraint that they have is the hereditary condition on atomic sentences. If A is less than or equal to B, and I've come to think of that, and others have too, as an information order. So A contains less information than B, and P, an atomic sentence, is true at A, well then P better be true at, and that's a typo, I'm sorry, B. So if it's true at A, and A is less than or equal to B, it continues to stay true as you get more information, and it's true at B. It can be shown by induction. This extends as well to compound sentences. The hereditary condition is needed to show that the value of phi arrow phi at the distinguished world 0, that's where all the logical truths are supposed to be true, is true. Now, for the sake of ready comparison to the clauses for arrow logic, we assign to each atomic sentence a set V of P, subset of K, just like with arrow logic, V of P was a subset of the set of arrows A. And we write X turnstile phi rather than I of phi at X is true. The hereditary condition then just amounts to requiring that V of P is a cone, i.e. if A is a member of V of P and A is less than or equal to B, then B is a member of V of P. That time I got it right. I got the B there. The Rotley-Meyer evaluation clauses now can be stated as follows. X makes P true just in case X is in the V of P, as the setups assigned to P that where it was supposed to be true. X makes Morgan negation phi true if, of course, something about not X making phi true, but we switch to X star. It's not X that's false at phi, it's X, sorry, it's not phi, where phi is, I'll say it again, it's not X star that fails to give us phi, it's, I can't talk this morning, sorry. It's not X that fails to give us phi, it's this other funny world, X star. And people written quite a lot about that and tried to make sense out of it. And I think it does make some sense, but I'm not going to lead you through that here. X makes phi and psi true, just in case X makes both phi and psi true. X makes phi or psi true, just in case X makes at least one of phi or psi is true. And then X makes phi arrow psi true, just in case for every y and z, if you have R, X, Y, Z, and Y makes phi true, then Z makes psi true. And I have a way of looking at this, which I've written about, which is that you think of this, X is basically a subscript. We're thinking of a relation, R sub X, right? And we're basically saying that you're at a state X, where that if the machine were to go into state Y, then state Z would be a possibility, kind of a relativized accessibility. And Graham and I were on a paper with how many authors? 11?
11, 2 of them dead.
Yeah, where we explored things like this. So anyway, here's the high point. The list of the apparent differences between the arrow frames and the Meyer frames. And so you probably know Dave Letterman's top 10 list, right? So this is a list of the apparent differences. And what I'm going to show in each case is that you can fiddle with it and the difference disappears. So that the essential moral of this talk is that arrow frames and Meyer frames are the same things, but in different notations, motivations, and so on. So difference 1. Van Bentham formulates arrow logic without disjunction and with connectives for the classical conditional and the classical equivalence not present in the relevance logic. Fix 1. Phi or psi can be defined in the usual way using the Boolean negation, as De Morgan way, right? Not the case, not phi and not psi. And once we get to the next fix 2, we can add Boolean negation to the Meyer framework. And then the classical conditional equivalence can be defined in this expanded language of relevance logic in the usual way too. So this brings us to difference 2. The Meyer framework was missing a Boolean negation. It had that funny De Morgan negation, right? The tilde negation that used the star operator to define its truth. Well, fix 2, fortunately there's a well-known way to add Boolean negation to relevance logic. Meyer and Routley have shown how to convert an arbitrary one of their models into an equivalent Boolean model. And you will follow this, but I just want you to know that there is a trick, which is to add a new element 0 prime to replace the old special world 0 and define a new star prime that's like star, but it takes the new 0 to itself. So it's star of 0 prime. It should be 0 prime. And there's a new relation R prime that's like R, but you have to define when 0 prime holds in this new relation. And you define R, I'm just going to say it, R prime 0 prime A B if and only if R prime A 0 prime B if and only if A equals B. And also you have to define when 0 prime holds at the end, and we'll say R prime A B 0 prime just in case A equals B star. There will be no quiz on this, don't worry. It works. I mean, I think that's the main thing to say. And you can add Boolean negation, and you can then get various relevance logics, like especially the system R of relevant implication, with a Boolean negation added. Difference 3. The Van Bentham framework is missing a De Morgan negation. Well, this can be fixed too. Meyer suggested adding star as a unary connective in relevance logic. Remember, it's an operator on a frame. We'll define x satisfies star phi just in case x star satisfies phi. You don't know what it means, but it makes obvious sense, right? Remarking that in fact it already exists in Boolean's relevant logic, and since we can define star as a operator by Boolean negation, De Morgan negation phi. That operates just like the star operator we want. That star will make that true just in case, sorry, that x will make that true just in case x star makes phi true, just as desired. Bob then also observed that De Morgan negation need not be taken as primitive, but can be defined. So you can define tilde phi as the Boolean negation of star phi. Star is much like converse, so the same trick allows us to define a De Morgan negation connected within arrow logic. Tilde phi is Boolean of the converse of phi. So I've started to use instead of the V, I started to use a more subtle and more usual looking converse sign, right? As we are working on the Meyer frames. Now, the main point is that you can define a De Morgan negation in the Van Bentham framework. Difference 4, the Van Bentham framework is missing a relevant implication connective. Well, it's been known actually since my dissertation that instead of having implication as primitive in relevance logic R, one can instead use a binary connective. It's been given various names, dot there. Cotenability is what I called it the first time. Intentional conjunction. Bob Meyer came up with the name fusion, brilliant name that's most often used. There was Girard in his linear logic talked of something similar, multiplicative conjunction. Anyway, one can define phi arrow psi to be the De Morgan negation of tilde psi fuse phi. So it's essentially sort of saying that phi doesn't imply not psi, but it's twisted around so as not to build in commutation. That's why it's tilde negation psi fuse phi. One can do the same thing with Van Bentham's dot, is multiplication of relations, now using the De Morgan negation we found hidden in his framework in fix 2. So then you can get that y makes phi arrow psi true if you define it that way. Just in case for all c and x, if c, x, y, z, x is the composition of y and z makes phi true, then x makes psi true. And this transliterates the Rutley-Meyer clause. So basically, you can add what's missing, the relevant implication to the Van Bentham framework and the De Morgan negation to the Van Bentham framework. And we've already shown how you can add the Boolean negation to the Rutley-Meyer framework. Difference 5. Rutley-Meyer framework is missing the star connective. You guessed it. Oops, that is another typo. Should say the Rutley-Meyer framework is missing the dot connective, the multiplication connective. And you guessed it, we can do the dual of fix 4 and define phi dot psi, that's what it should be, not star, phi dot psi, to be the negation of psi arrow not phi, where those are tilde negations, De Morgan negations. Arrow 6, difference 6. Arrow logic has the constant sentence id, identity, whereas relevance logic does not. Well, it has become very common, again this is since my dissertation being a bit moi, to add the constant sentence t to relevance logic. As we shall see, fix 9, it can be interpreted just like the identity sentence of Van Bentham. Difference 7. Rutley-Meyer requires that V of P is a cone, whereas Van Bentham does not. So once P got to be true, right, it always stayed true. It points to have more information. Fix 2 has already taken care of this because an important side effect of that was to make less than just become equal. There is no strict less than anymore, it's just equal. So we get a cone degenerately because if A is less than B, well, it really means A equals B. And if A is in V of P, well, then B is there too. It's the same thing. Difference 8. Van Bentham framework contains the binary relation F, whereas a Rutley-Meyer frame does not. Well, we can define fxy as x star equals y. That's basically to say the converse of x equals y. It's easy to see that x makes star phi if and only there is a y, such that fxy and y makes phi true. And that's exactly what we need to get a relation that behaves like f. We're getting close. Difference 9. The Rutley-Meyer frame contains the operator star, whereas the Van Bentham frame does not. This is in fact a real but small difference. As we saw above, Van Bentham seems to accept frame I guess we didn't see that though. Anyway, Van Bentham actually, his first 3 conditions he lists as possible conditions you might want on an arrow frame are those that are required to make f an idempotent operation. And these in effect make f an operation which he denotes as tau. More importantly, it's known the star operator be replaced with a binary compatibility relation. This was, you can see papers by myself, Meyers, and Rustel. And so the basic idea is if you're willing to put just a few postulates beyond the minimal arrow logic axioms, those that are required to make the F a unary operation and an idempotent one, which means that X star star is X, then this is not a real difference. Difference 10. An arrow frame has the set I subset of W, whereas a Routley-Meyer frame has only the single element 0 a member of K. Well, fixed 10 has become very common to replace the single 0 with a set of zeros, Z. And any of us who've worked on the algebra of relevance logic started doing that a long time ago, because Z acts like an identity element on the monoids that are studied when studying relevance logic. For example, the Morgan monoids for R. And this can be used as the interpretation of the propositional constant T. If you look at the worlds in which T holds, right, they'll be just the worlds in this set Z. So all the differences, right? I'm reminded of you in sleight of hand, but we have a difference and then it disappears, and a difference and then it disappears, and so on. They're not real differences that are any mention, real mention, other than perhaps the fact that Van Bentham has no requirement on the relation F, but he mentions, I said, right away, the first three postulates, and he'll assume these from now on, are that it is essentially a unary operator that's an involution, period 2. Okay, we're representing relation algebras using Routley-Meyer frames. There's a standard axiomization of relation algebras due to Tarski. Well, Linden, 1950, showed it incomplete with respect to the intended interpretation of relation algebras as sets of relations, sets of ordered pairs, right? Now, this is in sharp contrast to what happened with sets. Boole put forth his algebra, right, as an algebra characterizing sets, also propositions, but sets, the fundamental interpretation, the primary interpretation. And somewhat later, we have the proof that every Boolean algebra is isomorphic to a field of sets, right? This is the famous Stone theorem, right, of 1935. So this intuition that Boole had, that he was axiomatizing sets, the properties of intersection, union, and complement, came out to be true. Every abstract Boolean algebra is isomorphic to such a collection of sets closed under those operations. You might have thought the same thing would happen for people like Hamilton and Peirce and so on, who are working on relations and the algebra relations, that it would turn out their tuitions in due time would be shown to be correct, and somebody would prove the wonderful theorem that you write down a set of axioms for relation algebra, which Tarski thought he did, I think, and then you show that every abstract relation algebra is actually isomorphic to a concrete relation algebra, where the relations are sets of ordered pairs, right? Wonderful idea. But Linden, in 1950, showed it wasn't so. He showed that the standard axiomization of relation algebras is incomplete with respect to the intended interpretation of relation algebras as sets of relations, as sets of ordered pairs. Now, I showed, got two dates here because the publication was delayed. It was in a volume honoring Church, and unfortunately it was supposed to be honoring Church when he was alive, and then he died, and then it became a memorial volume, and that took some redoing. And so the 1993 paper date I have there is from a research report from the Logic Group at Indiana University. 2001 is when the book in memory of Church actually came out. Anyway, I showed that the Tarski axioms are complete with respect to their interpretation in a natural class of Routley-Meyer frames. So this may seem a little technical, it is, but then we'll go on to see a more intuitive interpretation that gets us back to relations and sets of ordered pairs. So here are some conditions on a Routley-Meyer frame. A frame is associative whenever you have that RABX and RXCD. That means then there is some x, so you have RAXD and RBCX. And what you want to think of BCX, that means sort of BC together are included in X somehow. So when you have RAXD, that means that you can sort of put the BC where the X is, as it were, and you get RA parentheses BCD. So it's kind of associative. The RABX and RXCD is sort of saying RAB together CD, whereas the other side, RAXD and RBCX, is kind of saying A and then BC together, D. And that's why it's called associative. A frame is assertional if there is a Z, so that you have RZ AB, if and only if A equals B, if and only if there is a Z, so that RAZB. So basically we're saying that Z functions as a set of quote-unquote zeros. If you have RAZB, that's because A equals B, and vice versa. And then the same thing, but where you put Z in the second position. An involution is a unary operation on U, so that for all A and U, R, A, inverse equals A. An involution satisfies tagging if RABC implies you switch the B and the A and you leave the C where it is, but you put the converse on them all. So RABC implies RB converse, A converse. We switch the A and the B, and then C converse. And an involution satisfies antilogism if you have the biconditional RABC if and only if, well, again, there's some switching around to do. You move the A out of the way, you put a converse on the C and put it where the A used to be, and then you put a converse on the B and put it where the C was, move it to the end. So, yeah.
Say something about where that name comes from?
Christine Ladd Franklin. Do you know who she is? Famous, in some circles, woman philosopher in the early 20th century. She's had some principles of logic, one which was something like if A and B implies C, then A and not C implies not B. So it's, and you know, the antilogism I think actually comes from medieval times, something to do with the syllogism, right? I'll tell you one story about Christine Ladd Franklin. She's alleged to have written a letter to Bertrand Russell that said, yes, I read your book, Introduction to Philosophy. I enjoyed it a lot, but you know, you claim that solipsism is wrong. I've never understood why everyone isn't a solipsist. So anyway, but she's a very bright woman. So that's it. The representation theorem I gave was that every relation algebra is isomorphic to a relation algebra defined on subsets of an associative assertional frame on which is defined an involution satisfying tagging and antilogism. Isn't that intuitive? Now, we're going to make it more intuitive. Define R sub A, just to be the set of pairs xy, so that RAXY. It's a set of ordered pairs xy such that AXY. It's then straightforward to see that this establishes a representation where the subsets I on the frame, I'm viewing the subset of a frame as a set of indices, are interpreted as sets of relations. So we have the set of relations R sub I, so that R sub little I, so that little I is a member of big I. Meet and join are interpreted as intersection and union. And converse is very easy. If you have an index set of binary relations, you want to form the quote-unquote converse of that set of binary relations, just form the converse of each one individually and take the set of those converses. So we have converse operating one type level higher. It's not operating on relations, it's operating on sets of relations. And the way it operates upon a set of binary relations is to dig down in to the set, take the individual relations and make their converses. Okay. Multiplication. You've got two index sets of relations. How do you find their multiplication? Well, it's the same idea. We know what the multiplication of two binary relations is, right? You have rxy and syz. The multiplication is when both hold, when there is a y, so that rxy and ryz. So we do the same thing here. If you want the two sets of relations and you want to take their multiplication, you go down and take the individual multiplications of each of the binary relations from the first set with one from the second set in all possible ways. And that's the way the multiplication is defined. Okay. Now, informally, we are up a type level from the original desired interpretation in terms of relations. Elements of an abstract relation algebra are represented not by relations, but rather by sets of relations. Deference of computer science, a relational database. So, and converse and relational product are being interpreted as I just illustrated point-wise. So that's a kind of odd representation. It's sort of like the original intuitions were right, but just off a type level. And we do get a representation of relation algebras using relations, but they're down one level. They're within a relational database. And so that's the representation. And now the nice thing is, this representation, because of the equivalence that I was giving, is shared by relevance logic, and if you write down the sufficient axioms, it's shared by arrow logic, right? And I don't know, there are more technicalities here. It's sort of more on my top 10 list, as it were, but drilling a little deeper. There are some small but notable differences between the frame conditions for the Meyer frame I just listed: associativity, assertional, involution, and those of Van Bentham listed above. Van Bentham's 2.1 to 2.3 are equivalent to take the converse to be an involution, and I've already talked about that. Those are the conditions on F. It's easy transliteration to see associativity is the same as Van Bentham's frame condition 2.8, and we'll talk more about this. And tagging is the same as frame condition 2.4, and actually we won't talk about it. It's just easy. You just look, and then they're exactly transliteration, associativity. Sorry. You can get exact transliteration of associativity and exact transliteration of tagging. So we're left with conditions 2.5 and 2 to 2.7. And here they are. I think I'm just going to skip over this. If anybody doesn't believe me, right, I can send them the slides. But the basic idea is that Van Bentham has a condition 2.5 CXY. Sorry, I've got to back up. What is this a condition for? He starts writing down conditions that he thinks are conditions that would hold of relation algebras, right? And he never, to the best of my knowledge, says, oh, this is a complete list. But he says these are correspondences. These are things that will force certain conditions on the frame, right? And 2.5 says CXY implies CZ tau y x. And that transliterates with one of the Meyer conditions. RYZX implies RY converse XZ. And then you just show by tagging an antillogism and involution that you can get the Van Bentham condition from the Meyer condition. 2.6, that if x is an identity arrow, then its converse, tau of x, is an identity arrow, frankly threw me for a bit. I was in mild panic. But you can easily get it once you see what you're doing using involution and the assertional aspect of a frame and involution. And then the condition that Van Bentham has that if y is an identity arrow and you've got x is composed of y and z, that x equals z, that transliterates with a frame being assertional in an easy way. And then you've got to go back the other way. Got to show that some the Meyer conditions that I put on, like being assertional and being associative, and so on, that you can get those from the Van Bentham ones, and it turns out you can. And I think I'll just leave it at that. But there's one little technicality here. Van Bentham considers the axiom that essentially says the identity relation multiplied by x is less than or equal to x. He does not consider, and I don't know why, the converse, that x is less than or equal to the identity multiplied by x. And that corresponds to a condition. There is a z, RZAA, which I simply haven't seen in his writings. Patrick, you might be able to help me. But so the feeling I get in reading Van Bentham is, and you can find something similar in Venema, is they're writing down things that are nice, things they think might define relation algebras, but they have no clear sense, no clear statement that, these are the requirements that will give you a representation of relation algebras. I just don't see that. And Van Bentham, at least, it seems to me, has missed by a hair this one axiom that basically says x is less than or equal to id times x. And it's the one that corresponds to, in the Rottley-Meyer framework, there is a z, RZAA. And I think that we, in effect, have shown here that you can give a completeness proof for the Van Bentham arrow logic with essentially all the axioms that he wrote down, if you only add one more, which is that x is less than or equal to id x, or phi implies id dot phi. So I now have a conclusion, and I think the conclusion is probably more or less what I just said. I'm not going to ask you to read all that on that small screen. You might wonder, though, what is the basic difference between the postulates I put on a Rottley-Meyer frame to get us the representation theorem for relation algebras, and the Rottley conditions on a Rottley-Meyer frame that gave, say, the system R of relevance logic, and the answer is 2. The system R of relevance logic requires total reflexivity, RAAA, and that's not true in our for relation algebras. It also requires commutivity. RABC implies RBAC, and this is not a property that would hold on a frame where one was trying to axiomatize relation algebras. And on the other hand, this tagging, which is so valuable in the representation of relation algebras using Rottley-Meyer frames or all but the relational databases, that doesn't hold in the Rottley-Meyer framework for relevance logic. I mean, it's not one of the standard axioms. I had to sort of see it and say, what happens if you add that? So, and I think I'll just leave it go. That's where I say I believe we've answered a question implicitly left open by Van Bentham, which is the completeness of the Tarski axioms for relation algebras using his arrow frames. And, some references. I guess it's hard to see that bottom one, that's Venema. And let me close by saying I and my wife Sally I want to thank Mel and his wife Roma, neither of whom, Sally or Roma, are here right now, but still, for a wonderful time spent with them, including this conference. Thank you again, Sergey. And I want to thank Mel in particular for two things. His work on bilattices, and his credit to me for work anticipating the representation, work done in the beginning of my career. I could barely work on one lattice, certainly not two at a time. And also, most important, is telling me about orthotics. Does everybody know what an orthotic is? Yeah, many of you are probably too young. But at a certain point, if you, in your career, if you are going to various conferences, walking around big cities, you'll want something like that. And Mel told me about orthotics, and I have taken his advice and valued it ever since. And as I said, I had worked on ortholattices, but orthotics are different, and they help more with walking. So Mel, Sally, and I look forward to seeing you in Roma at more conferences now that you are on permanent research leave and can travel. That's it. Thank you.
Just a comment, it's rare to hear a talk with a real footnote.
Thank you. I got a letter from Alan Ross Anderson, whom I had not yet met. He came to Pittsburgh when I was a student later, but where I had written a paper which I'd sent him on negation. And he'd written on negation, and I wrote kind of amusing response. And he said, I got the credit for the first referential footnote, so maybe I should form a society of footnoters.
Yes, please.
I have a question. So you mentioned the analogy with the stone representation theorem including algebras, and that argument, of course, uses a lot of ultrafilters
Yes.
and the axiom of choice.
Right.
But in the representation theorem that you gave, I didn't see any ultrafilters. Is there any expectation that choice would...
Oh, actually, on the very end, it talks about you have to show the existence of ultrafilters or maximal filters, maximally consistent sets, whatever.
Yeah, I see.
And there's something that Bob Meyer created called the squeeze lemma, which is very good for showing the existence of maximal consistent sets, ultrafilters. And yeah, you have to use that here. And that's, I think, why Johann van Bentham did not do a representation theorem or completeness theorem, because he all of a sudden focuses in on 1.0. Let's look at the sentences that are only universal, right? And for example, the minimal error law, all those were just, A multiplied by B join C is A times B join A times C, that sort of thing, right? There wasn't anything like there is a Z, so that our ZAA, or he even disparages associativity a bit, right? And that required, there is an X of one sort, then there's an X of another sort. So all those things require, axiom of choice.
Time for one more question. Well, let's thank the speaker again. And we'll probably have technical 1-2 minutes break.